Welcome to this unit on operating with dimensions. And by operating with dimensions, I mean like what math can we do with quantities with different dimensions. So let's start out talking about addition, subtraction, and equality. It's the same rule for all of those things. Quantities must have identical dimensions to use plus, minus, and equals on them. So in other words, there's no such thing as what is 2 meters plus 5 seconds. If I ask you that question, you say, well, that's nonsense, right? That's sort of mathematically illegal. If I say 3 hectares equals 7 joules, you say that's impossible. Hectares are a measure of area, joules are a measure of energy. It doesn't make sense to compare those things, just like you can't add together a length and an amount of time. Okay, things that are legal are things like 10 grams minus 8 grams. Those are the same dimension, and in fact, they're even in the same units. 3 seconds plus 2 hours, well, that's also legal, right? Those are both amounts of time. If you want to write that as sort of one compact number, you're going to have to convert one of those quantities, and we'll talk about that in another screencast. Here's another quick example. If we say y equals ax squared plus bx plus c, and the dimensions of y are length, and the dimensions of x are a mass, then we can ask what are the dimensions of a, b, and c. And we can use the fact that all of these quantities have to have the same dimensions to figure it out, right? And when I say all of these quantities, I mean ax squared has to have the same dimensions as y because they're compared with an equal sign. Bx has to have the same dimensions as y because they're compared with an equal sign, and so on. So let's just write this down. Let's start with c. The dimensions of c have to equal the dimensions of y because those two quantities, c and y, are on opposite sides of an equal sign. And we know that the dimensions of y are L, so the dimensions of c are L. Now let's look at this term, bx. We know that the dimensions of bx, which are the same as the dimensions of b times the dimensions of x, which are the same as the dimensions of b times m, because we know the dimensions of x are m, we're told that. We know that those dimensions of bx must equal the dimensions of y, right? Because they're compared by an equal sign, and we know those are L. So if we compare this and this, we can write that the dimensions of b equals L divided by m, or sometimes we'll write it as Lm to the minus 1. Okay? And as the last part, we can ask what are the dimensions of a x squared. Well, we know that the dimensions of ax squared would equal the dimensions of a times the dimensions of x squared. That's the dimensions of a times mass squared. And that has to equal the dimensions of y, which are L. So we have dimensions of a times m squared equals L. So the dimensions of a will equal L divided by m squared, or L m to the minus 2. Right? So this is how we've used sort of addition, subtraction, equality to figure out what the dimensions of certain quantities are. Multiplication and division can be used on quantities with any dimensions. So it sort of is like anything goes here. Velocity is displacement divided by time, so the dimensions of velocity are Lt to the minus 1. Acceleration is velocity divided by time, so this should say acceleration. Dimensions of acceleration are Lt to the minus 2. Force equals mass times acceleration, so force equals m times Lt to the minus 2, and so on. You've actually been using this rule in previous screencasts. I just wanted to make it explicit here. Two other good quantities for you to get familiar with are work. Work is a force times a displacement. So that would be force, which is mass times acceleration, mlt to the minus 2, times a length, a displacement. So work has dimensions ml squared t to the minus 2, and power is another really good one to know. Power is work divided by time. Work's the same as energy, so another way to think of this is like energy per time. And so power is like a measure of your light bulb. How much energy does your light bulb use every second or every hour? Okay, so power is work ml squared t to the minus 2 divided by time. That's ml squared t to the minus 3. Exponentiation. Okay, I'm going to read you the rule. It's kind of wordy, and then I'm going to go through examples, which I think will make more sense. If a dimensioned quantity is raised to an exponent, the exponent has to be dimensionless. Additionally, if you're exponentiating a dimensioned quantity and it would result in a non-integer power of some dimension, then the base also has to be dimensionless. Okay, so let's make that very concrete with examples. If you take the quantity 4 kilometers, that's a dimensioned quantity, and you square it, you square everything. So 4 squared is 16, kilometers squared is square kilometers. 16 square kilometers, that's a quantity that makes sense. If you do 4 kilometers to the 2 kilometers, so now I'm trying to exponentiate to something that carries dimensions in the exponent, that doesn't make sense, because for instance, what are kilometers to the kilometers power? It doesn't make any sense. You can't do that. Okay, here's another example. Here we're exponentiating. Square root, you can remember, is an exponentiation. Square root is the same as something to the 1/2 power. So if I ask what's 16 square kilometers to the 1/2 power, you take the square root of everything. Square root of 16 is 4. Square root of kilometers squared is kilometers. That makes sense. 4 kilometers makes sense. If you take the square root of 4 kilometers, you're not allowed to do that, because you would end up with a quantity, right? The quantity you would end up with is 2 kilometers to the 1/2 power. Kilometers to the 1/2 power is a non-integer power of some dimension, right? This is dimensions length to the 1/2. That doesn't make any sense. What are square roots of a kilometer, right? So this is the rule. Transcendental functions, right? So transcendental functions are things you learned like sine, cosine, exponential function, logarithm, and so on. And the rule is that the input to a transcendental function also must be dimensionless, right? And so if you have a function like e to the kt, where t has dimensions of time, it must be true that the dimensions of that number k are t to the minus 1. Right, so then the product kt, right, that has dimensions t times t to the minus 1, that's dimensions of 1, that's dimensionless. You can only take e to the overall something that's dimensionless. Sine of 3 hours, here's another example. This makes no sense, right? You can take the sine of 3, but what is the sine of hours? It doesn't mean anything, you can't do that. And you'll often encounter in math texts examples or expressions like sine of 2t. And in order for this to make sense, if t represents time, then the quantity 2 must mean 2, and it must carry dimensions of time to the negative 1, right, per time. So I think a better way to write this is something like sine omega t, where omega has dimensions of time to the minus 1. So the big message here is transcendental functions, the overall thing that you plug into the function cannot carry dimensions, right? T can have dimensions, but then it's got to get multiplied by something that cancels out those dimensions. So this is the end of this short lesson. I want you to ask yourself if you can do the following things. With dimensions, can you apply the rules for plus, minus, and equals? Can you apply the rules for times and divided by? Can you apply the rules for exponentiation? Can you apply the rules for transcendental functions? And finally, can you use some of these rules to deduce the dimensions of certain quantities that might appear in an equation? All right, thanks for listening.